Hello everyone, I'm Harshitha Challa, student researcher at University of Cincinnati, here to present our research, Faulty Requirements Made Valuable, on the role of data quality in deep learning at the International Workshop on Artificial Intelligence and Requirements Engineering. So the main idea and contribution of our paper is that data are important requirement for deep learning. And instead of just specifying requirement false, we need to find innovative ways to cope with the data false. The chief contribution of the paper is to embrace the faulty data in new ways instead of eliminating the faulty requirements altogether. And to substantiate this, we carried out a case study with the Metropolitan Sewer District of Greater Cincinnati, MSDGC, where the prediction of combined sewer overflow is experimented with recurrent neural networks and time series data by altering the stationarity of the time series data, which is an important data quality attribute. We elaborate on the notion of data being an important requirement by looking at the requirement falls and Jackson's foundational work on the environment and machine. According to Jackson, requirements are located in the environment and they do not directly concern the machine. They concern the environment in which the effects of the machine will be observed once it's deployed. And this figure here contextualizes requirements as problem theories. And a specification, that is the SRS, bridges the problem and the solution. It talks about the functionality, interfaces, design constraints, etc. Specifying these requirements is prone to human error because of things like lack of attention or inadequate planning, etc. And these manifest in an SRS as requirement faults. And these faults, if not detected, could lead to failures of the machines and can be costly to rectify in some cases. And so proper inspection has to be employed to ensure the quality of the requirements. And when we look at the data quality in deep learning, checking data quality in the same static manner as inspecting SRS is no longer appropriate. If we look at Jackson's work again, deep learning models can be contextualized as the machine. We know that all the internal parameters, hidden layers, models, etc. belong to the private part of the machine. But if we look at the applications like board games, speech recognition, etc., they overlap the environment and the machine. This is because no matter how the machine is built, its effects have to be observed in the environment, say by competing against human players in the case of board games. The training data exists without the machine, so it's not in the private part of the machine. And the same training data influences the deep learning model's behavior, so it is not the private part of the environment either. And that is why data is positioned in the overlap of the deep learning machine and its environment. Deep learning models are data hungry and require high quality input data to train to make good prediction. And data quality can be viewed as inherent or system dependent. We focus on the inherent attributes as the system dependent attributes depend on how the machine handles the data. So if you look at the inherent data attributes, we have the accuracy, completeness, consistency, credibility, and currentness. And in our work, we look at consistency, where data needs to be coherent with each other. Example, we explore the concept of stationarity. And we also look at currentness, that is the degree to which data is of the right age. And all these characteristics of data are very different from the usual requirements. And that is why we cannot use static methods similar to normal SRS inspection. And so we propose a new kind of metamorphic testing approach by making data faulty and observing the machine's behavior. In general, metamorphic testing is used when there is no oracle. There is no way to check if the machine is giving the expected output. For example, we do not know the answers for scientific calculations. And in our work, we explicitly create faulty data based on the inherent data quality characteristics that we see here and observe how the accuracy of the machine drops. In our case study, we collaborate with MSDGC addressing combined sewer overflow problem. And this figure here illustrates the combined sewer system. It manages stormwater runoff, domestic sewage, and industrial wastewater. And overflow occurs when the volume of wastewater exceeds the safe capacity and untreated water is discharged into the water bodies. So this is an important problem to be dealt with. SCADA, which stands for Supervised Control and Data Acquisition, is deployed by MSDGC to collect large amounts of data through sensors in the sewer pipes. And MSDGC's smart sewer system covers 150 square miles and 164 overflow points. And we pick one of these overflow points for the case study, and the data looks similar to the table seen here. We have attributes like flow, velocity, and level, and these are being recorded at every timestamp given. It is seen that RNN is the best deep learning model for time series prediction, especially for overflow forecast, and so we choose RNN for the case study. To understand how we use metamorphic testing in this case, let's dig into the concept of stationarity, which is an important characteristic of time series data. A time series is stationary if the statistical properties of the time series, example the mean and the correlation coefficients, do not change over time. And a time series is weakly stationary if both the variance and the mean are constant. For example, here, if you look at the first diagram, the values of stationary data do move irregularly, but eventually they revert to their original mean, which remains constant. Whereas if we look at the second diagram, the mean of the non-stationary data varies. And for multivariate time series, cointegration values can be used to test stationarity. High cointegration level means that one or more linear combinations of multivariate time series is stationary, even though individually they may not be stationary. And so if time series are cointegrated, they cannot move very far away from each other. And this is a key to data consistency. For our experiment, we constructed an LSTM RNN machine with 3 hidden layers each of 10 neurons and 1 dense output layer with ReLU activation function, SGD optimizer, 0.01 learning rate, and we ran it for 10 epochs with batch size 1 and with 5,000 timestamps of training data size. And we did 2 rounds of testing, one with the original test data and the other with the stationarity of the test data altered. And to alter the stationarity, we apply linear transformation on the attribute flow that we saw in the table by using the equation given here. Here, the change in variance of only one variable will alter the stationarity of the data. We then measure this change in stationarity by change in cointegration, and we measure the error of the model to quantify the performance, that is, difference between the original and predicted values for all the variables. In the results, we find a general trend, that is, when cointegration decreases, which means we have less stationary data, the error increases, that is, we have lower accuracy. And we see that the cointegration mostly decreases when the operation is performed. This indicates that the metamorphic stationarity change makes the data worse rather than better. For example, in these 2 pictures that we see, we have the metamorphic change in both cases reducing from 0 up to minus 140, and in the second case to minus 200. And one practical implication is that the data has to be stationarized before feeding into the RNN. Another implication is that users shall select the data representing the context more stably. And to investigate this, we perform another experiment where we train 2 RNNs, one with 4-month more current data and another with 2-month less current data. Say the first one is recorded from January to April and the second one is just from January to February. We test it again after applying the metamorphic stationarity change, And we see that the model with less current data produces more noisy results. And if we take the ratio of y and x-axis over here, that is, say, the slope of the graph, we find that the first model has a smaller range of, say, -1 to 1, but the second one has a wider range due to more noise. Practically, these threshold ranges can be used to inform MSDGC engineers about the RNN behavior, about its limits, and if human intervention is needed. Threats to validity. The internal validity can be influenced by, say, the hyperparameters of the model, that is the way it is implemented, and also the specific parameters in linear transformation used, that is the constant values in the metamorphic stationarity change equation, and also the attributes that we choose, that is the flow or the value, etc. And also selection of training and testing data. And if we look at the external validity, the results may not generalize beyond the multivariate time series data and the prediction context of combined Seaver overflow. In conclusion, this paper presents our view that deep learning machines require special attention to data quality requirements, and static data quality checking is no longer appropriate. And we define a novel set of operators based on metamorphic testing to directly alter data quality. And we illustrate this with testing of RNN under metamorphic stationarity change of MSDGC's time series data. Our work exploits faults in software and system engineering to create new ways of taking advantage of these faults in requirement engineering tasks. And we see that the experiment results reported have linked time series stationarity with data currentness. Future work may help assess multiple data quality requirements for deep learning. Thank you.